Alright guys, today is day 105. Today we're going to learn from section 5.4 the second fundamental theorem of calculus. And your homework is in that section, page 303, 27 to 40. So hopefully by now you have worked with your classmates to answer the problems on the quote-unquote baby integrals worksheet. And let me just kind of go over the answers for you right here. This one's demonstrating the power rule and the constant multiple rule. So I'm going to bring the 8 out. Then I'm going to work on x to the 5th. The power rule says make the power 1 higher and divide by that new power. I can actually simplify the 8 and the 6, and that becomes 4x to the 6th over 3 plus c, your constant of integration. Don't forget that. All right, number 2, if I rewrite this like 8, the integral of x to the negative 5, which is really what that is, the constant multiple and x to the negative 5, you're going to see the answer is 8x to the, well, I'm going to add 1. Don't forget you're adding 1. A lot of people think this is going to be negative 6, but add 1 and it goes to negative 4. Divide by that new power. I can now divide 8 and negative 4, get negative 2, x to the negative 4 plus c. And actually we'd write this really like negative 2 over x to the 4th plus c. All right, number 3. Keep our 8. Once again, our power goes up. So our power goes up by 1. So 3/5 plus 5/5, which is 1, is going to be 8/5. Now I'm dividing by 8/5. If you divide by a fraction, you multiply by the reciprocal, and the reciprocal of 8/5 is 5. Let me erase that for a second. Is 5 over 8. So dividing by a fraction is like multiplying by the reciprocal. Cancel the 8's, and you get 5x to the 8 over 5 plus c. And if at any point in time you're not sure, you think this is weird, take my answer, take the derivative of my answer, and you should get back the integral. All right, this is the same kind of problem. I'm going to rewrite this 8 integral of x to the negative 3/5 dx, right? 8's still there. X to the negative 3/5 becomes x to the, let me add 1. Negative 3/5 plus 5/5 is 2/5 divided by my new power. So divided by 2/5 is times 5 over 2. The 2 and the 8 cancel. This becomes a 4. So 4 times 5 is 20. X to the 2/5 plus c. All right, moving on to number 5. This looks really strange, but this is still just a power rule. That's pretty much the most powerful rule that you know so far. So this is negative 2 times the integral. I'm going to rewrite this like x to the 4/3, but that was negative. Okay, so my answer would be negative 2, x to the 4/3, so you're going to add 1. Adding 3/3 to that would make it negative 1/3. Divide by negative 1/3, which means, divide by negative 1/3, which means multiply by 3 over negative 1. And the negative and negative are going to cancel. So we've got 2 times 3, which is 6, x to the negative 1/3 plus c. All right, next one. Here, it looks a little crazier. We're going to have to simplify. There's actually no such thing as a quotient rule for integration like we're used to with the derivatives. So we have to simplify this first. I'm going to write this like this. Now, if I have u to the 1, which is basically what this is u to the 1 over u to the 4/3, right? We can simplify that by subtracting those powers. So 1 minus 4/3 is actually u to the 1/3. Haven't taken the derivative, just simplified. So this is negative 3 u to the 1/3 du. Okay. So my negative 3 is still there, constant multiple rule. Add 1, so that's 4/3. Divide by my new power, so that's 3 over 4. My negative 3 times 3 multiply. I've got negative 9 over 4 u to the 4/3 plus c. All right, negatives number 7. Once again, I did not teach you a product rule. There's no such thing as a product rule, so I actually have to multiply this out first. This is the same thing as the integral of 21x cubed minus 14z squared, dz. All right, so now I'm going to integrate those just like we did before. They're a constant times a power. So 21x to the 4th over 4 minus 14. Sorry, this was a z. I apologize. Z, that doesn't make any sense. I'm switching variables. Z, 14z to the 3rd over 3 plus c. All right, number 8. Let me just switch colors here, so hopefully it'll be a little bit easier for you to see. Number 8 is the same thing as the integral of 21p to the 7th minus 14p to the 4th dp. That tells me my variable. So that integral is going to equal 21p to the 8th over 8 minus 14p to the 5th over 5 plus c. All right, number 9. We have, looks like a quotient, but once again, no quotient rule. So I'm going to rewrite it like all these quotients added together. So this is the integral of 7a cubed over 4a minus 3a squared over a minus 3 over 4a. All right, let's rewrite these even. A's cancel. A cubed over a just becomes 7/4 a squared minus 3a minus 3/4. I'm going to say this is like 3/4 times 1 over a. I'm going to write it like that for you. The a. All right, so let's write this answer. This answer is going to be 7/4 a cubed divided by 3. So it's like I'm multiplying it by 1/3 minus 3a squared over 2 minus 3/4. And then if you remember, there's a special rule for this. This is like a to the negative 1. And if I use the power rule, I get a to the 0 over 0. So it's actually 3/4 times the natural log of the absolute value of a. That is just a rule that we have to memorize. That's the answer for number 9. Number 10, let me change colors again so we can do this. As you can tell, we're going to do the same thing. We're going to divide them all. All right, so let me kind of write this wherever I can. Number 10, the integral is going to become 7 over 4, and the root a's cancel, so 7/4 minus 3/4 a squared divided by a, root a, like we had up here. You're gonna subtract those exponents. So 2 minus 1/2 is 3/2. So that's a to the 3/2 minus 3/4, and I'm gonna write a to the negative 1/2 because that's really what it is. dA. Okay, let's do all of our answers. So 7/4, when it has no variable, it actually picks up the variable. So it becomes 7/4 a minus 3/4 a to the, let's add 1. So 3/2 plus 1 is 5/2 times 2 over 5, because I'm dividing by 5/2, minus 3/4 a to the 1/2 divided by 1/2, which means times 2. All right, let me just kind of clean it up a little bit. 7/4 a. Here I'm going to multiply across, so 2, although the 2 and the 4 will cancel, that'll be 1 and 2. So 3, so minus 3 over 10, a to the 5/2. And then once again, my 2 and my 4 will cancel, and that'll become a 2. So minus 3/2, a to the 1/2, plus c. And honestly, like I said, if you don't believe me, take the derivative of this and check it out. All right, so today, the fundamental theorem of calculus. We're actually going to do the second part first. But what is so fundamental about this theorem? And like you can see right here, you guys can read. But basically, before this theorem exists, there was no such thing as calculus. There was a bunch of people taking derivatives. And there was a bunch of people taking integrals, so people finding rates of change and people finding areas under curves. And what happened was they began to realize that these two topics were related. They were really doing the same thing but backwards. We grouped it together, and that's what created the concept or the idea of calculus. The connection started the mathematical development that fueled the scientific revolution and has really changed science. And it's still regarded as the most important computational discovery in the history of mathematics. So calculus is fundamental to mathematics. What does it do? Well, it has two parts. I think they're backwards, honestly, but what do I know? So I'm going to teach you the second part first, part 2 first, because it makes more sense to me to do it this way. So the second part is basically what I would think of as like the evaluation part, which it says right here, the evaluation theorem. It tells you how to evaluate an integral when you have bounds, how to actually take the antiderivative and the bounds and come up with an answer. So here's the theorem right here. If f is continuous at every point on a closed interval, which we know it has to be in order for it to be integrable, and if the big F, so I'm going to say big F, so if little f is continuous at every point on an interval, and big F is its antiderivative of the little f, right? So if big F represents the antiderivative, then the integral from a to b of the little f is big F of b minus big F of a, which means basically you take the antiderivative, you plug in b, the top bound, you plug in a, the bottom bound, and you subtract those two answers. Okay, so that is how we evaluate a definite integral. All right, and if you need to go back and pause, feel free, go ahead. Fundamental theorem calculus part 2, once again, it says it right here. The integral from a to b of f of x is big F of b minus big F of a. Any definite integral of a continuous function can be calculated without taking limits, like we've talked about, without calculating Riemann sums, and often without effort, as long as we can find an antiderivative. So this should actually make things easier for us. No more rectangles. So let me just do this one example, and we are going to obviously do tons of examples once I get back tomorrow. But evaluate this integral from -1 to 3 of this function using an antiderivative. So basically, I'm going to pretend the bounds aren't there for a second. I'm just going to ignore them. I'm going to write them. So I'm going to integrate this function just like I normally would, like we just did for all those problems. It's just a power rule. So if I integrate 3x squared, it becomes 3x cubed over 3. Okay, so that was 3x cubed over 3, and those 3's are going to cancel. If I integrate 1, like I said, if it's missing a variable and you're integrating, you're just going to pick up that variable, so it's going to be plus x. All right, now what happens here is this integral sign changes, it kind of morphs, and it becomes a straight line. The 3 is still up top, and the 1 is on the bottom. I'm going to take my 3, I'm going to plug it into my function, because this is really big F of x right here, right? So I'm going to plug 3 into my function, and it's going to become 3 cubed plus 3. So I plug 3 into the whole function, minus, now I'm going to plug in -1, and that's going to be -1, the quantity cubed, plus -1. This is like your f of b minus f of a. All right, let's just evaluate that really quickly. 3 cubed, 27, plus another 3, 30, minus -1 cubed is -1, plus -1 is -2, so 30 minus -2 is 32. And this number literally represents the area under this curve from -1 to 3. All right, good luck with your homework, guys.